Okay, so you all got a laptop and a circuit kit. This is the handout is nice and short, but there's the work involved is going to be fairly involved. You're just going to look at one circuit, which is pretty cool, and you're going to look at it from a number of different perspectives. So this is kind of like a capstone lab for what we've been doing for the last few weeks, culminating with Thevenin's theorem. You are going to explore modeling a complicated circuit with Thevenin's theorem, particularly with the goal of maybe trying to figure out what load resistor to choose to get the maximum power to the load. And you learn how you can do that in the assignment. Today you are going to use a model of the circuit that you get from Thevenin's theorem. And I think actually, we're just going to do the Thevenin's model. And then build a circuit. So you're not going to simulate it. You've learned how to simulate already. That's actually very useful. But another way to model a circuit is simplifying it using Thevenin's theorem, right? So you're going to take a circuit, find the equivalent of it, and then you're going to build the circuit and see how well your model, your Thevenin model, matches the behavior of the real circuit in front of you, right? So you're going to build this actual circuit, and you're going to compare measurements with your actual circuit at terminals A, B with your Thevenin model predictions. And you're going to use the actual values of your components. You have to actually measure the voltage. If it's 12.3 volts, you gotta use 12.3 in your Thevenin's theorem model. And if the resistors are different than what they say here, you got to use those resistor values. So you're going to be as close as you can get with your Thevenin model to your actual circuit. And then you're going to build the circuit. You're going to compute RL for maximum power, and then you're going to do some measurements and see how well that actually fits the criteria. So it's a great lab just to kind of explore the use of Thevenin's theorem in a real circuit situation. And you're doing some breadboarding, you're doing some measurements, and you're seeing how well the model approximates reality, which is what we're trying to do with circuits. Any questions? I know you're all up for it. I have total faith in everybody. We have a good time. Let me know if you have any questions. I do have a couple notes here that I was going to share, and I think I was supposed to make some modifications. Let me see if I need to start getting ahead of these things. On the data sheet, this relates to maybe trying to figure out how much power you could get from a battery or something. That's a practical application of this. And also, I wanted to request that you insert a photo of the breadboard in this lab. That's all very useful to document your work. Anytime you're working in an engineering situation, you want to take a lot of documentation of your work, so in case you have to go back and figure out something. You might have forgotten how you laid out the circuits and everything. So I need to do that under build the circuit. Maybe I did that already. Let's see. Yeah, I don't see that. So let's see. How about under step 3? Well, actually, after everything is actually working. Hey, Mark. Under step 4 here in part 2, I'm typing this. After everything is working, please insert a photo of your breadboard circuit here. Actually, two photos. Two photos works better. One of them, include voltmeter, and the other just a close-up of the circuit itself. It's not hard. Everybody has a smartphone. It's really easy to post photos and grab them and put them somewhere. So just throw them in there, and that will be a great reference for your work. Again, someday you may need to show this to some faculty at the university to prove that you did, certain labs, and all this kind of stuff will help you in the long run. Plus, it's just good practice to get into. The other thing I actually made a note for myself is that if there is more than 3% error, I say summarize your investigation. What I really want to say is show your research, not just summarize. Include screenshots of worked problems of breadboards of the simulation. So when you do this, if you do this right, you should have less than 3% error between your Thevenin model and your actual circuit. So if you do have errors more than 3%, I really want you to show your research. That means you have to do some error checking to do that. So show your research, not just summarize. Include screenshots of worked problems, of the breadboard, of simulations, whatever you might need to do to kind of resolve that, right? Part of being successful in circuits is really keeping an eye open for discrepancies in what's going on versus what we think should go on. And when you see those discrepancies, there are opportunities to kind of learn more about what's happening. So, of course, this means everyone's going to fudge their results so they get exactly the right answer. But take that an opportunity. The more you can research and delve into this, the better.
What were the two photos of the breadboard again?
What were the two photos? Basically, under step 4 of part 2, after everything is working, please insert 2 photos of your breadboard circuit here. One of them is one of them includes your whole layout with the voltmeter, and the other one's just a close-up of the circuit wiring, so I can see the wiring in case there's any. If you do have a weird result and you haven't figured it out, I can maybe look at your circuit and provide some feedback later if I can actually resolve it. But you got to get a close-up photo of the circuit components so I can actually see if there's anything weird. Okay, that's going to be the new data sheet. I'm posting that for people who come later. So anyway, have a good time. You're going to start with the analysis of the Thevenin equivalent circuit. Actually, you're going to start by selecting the components to build the circuit. It's going to have these 3 resistors in it. Make sure, because one of those is 470 ohms, there's a really common tendency to mistake a 470 ohm resistor with a 4.7 k ohm resistor. If you do that, you're not going to be within 3% of your predictions, right? So be careful about selecting the resistors. You're going to measure them, record those values, and then using those values, derive the Thevenin equivalent circuit. And then build a circuit. So if you stay focused, it shouldn't take too long, actually. And if you don't run into any difficulties, let me know. You can try using superposition, source transforms, or nodal or mesh analysis, whichever one you like. If you're not sure, you can use 2 of those methods to derive the Thevenin. Okay, looks like y'all are well situated. I'll walk around every now and then, see you.
Okay, so
Is there something I can film? Let's see.
I just want to make sure everything's correct.
Okay.
The detail now.
Mm-hmm. So you're
No, this one
finding.
here. Yeah.
Oh, the bottom line? Okay, good. You've got, so for Thevenin, did you combine these two resistors?
Yeah.
Okay, those aren't really in parallel though. How'd you combine them? With the parallel formula?
Why not in parallel?
Well, remember, parallel resistors have to be attached between the same two nodes. So like on both ends, like this end has to be attached together, and then this end would have to be attached together at the same node. But there's just voltage source in between them.
Oh, okay,
So they're not truly in parallel. I mean, they are when you calculate R Thevenin because you have a short there now, right? And so these collapse together.
okay. But if that was in series and I put like the result there,
If what was in series?
I mean, this isn't series right now.
No, they're not in series either. Series resistors have to be exclusively sharing the same two nodes. And here you have a point where they kind of come together, but there's actually a third branch there. It's only series if there's just one path for the current to go.
So you can't use like a voltage divider or something.
You know, you can't use any of that stuff.
So you can use
Yeah, you could use mesh. Source transform, I don't think is going to really help you because it's a kind of a mess here. Superposition could work. You know, you could turn off one source and leave one on, and then you might have some voltage dividers there you could look at.
Okay.
But yeah, if you turn this one on and turn that one off, then yeah, you have some interesting parallels there. That's kind of fun to think of superposition. It's an interesting tool, but yeah, or just use mesh. It's pretty straightforward. Or nodal analysis. You know, VAB would be voltage across the 470 ohm resistor.
Can you remove that 470 if you're doing because it's parallel with the Thevenin?
Can you remove it because it's parallel? Well, it isn't going to show up in your Thevenin model, but when you're trying to find the open circuit voltage here, you have to leave it in there, I think, because that could be pulling down the voltage from something else. So yeah, you would leave it in there. But like the fun thing is with superposition. Let me see if I can draw that. Let's see. You could see that with superposition, you could say, you know, if you turn off, see if that's any easier. If you turn off, it's kind of fun with superposition because it really helps you look at the circuit a lot of different ways. But if you turn off this top guy, yeah, and you essentially got this. I'm trying to find the voltage there. Well, now you can you see that these are in parallel now? Because they attaching, both ends are kind of coming to the same two nodes, right? This is one node that they're attached to. This is the other node that they're both attached to. Those are in parallel. So then you have a voltage divider from that component. But then turning on the other one, let's see. With the other one, you know, if you have this guy, and now you've turned off this guy, you've got, you kind of have to just draw it and see what it looks like and see. Let's see. So now VAB is from here to here, right? And you can kind of see, do you see any resistors in parallel on that circuit?
Yeah.
Which two? Yeah, those are in parallel, right?
And you do the same thing.
So you can combine these in parallel, and then you get a voltage divider for that, right? So, and then you can add those two results together, and you get the answer really truthfully, right? It's actually simpler than doing nodal or mesh, right? Because you can make more mistakes that way, right? So here, the voltage divider is, you know, this over this parallel plus this times that. And here it's this parallel over this parallel plus that times that. Yeah, so, yep. Question?
Yeah, when I'm pulling up my data sheet,
Yeah.
I'm not getting the same data sheet as everybody else.
Really? What?
And this is in Word, obviously. It's the same thing as I just done. It's even worse, actually.
What does mine look like?
Yeah, that's what everybody else has.
How are you getting something weird like that? That's crazy. It must be cached or something. If you open it up in a different browser, if you just take that link, sometimes it's annoying, like the browser will cache it and then you re-download it, you get this old thing. It might have been like from a year or two ago. Let's see, try Internet Explorer.
That's the lab net out there, right?
Mm-hmm. Oh wait, should be a doc. Should be a docx. Oh, that's the lab. Yeah, I see. I got the wrong one. So you wanted to do this.
Yeah, that's fine. That's fine. You have that.
Okay, let me see the folder.
It's not a big deal because Alex has it up on his, but I just thought it was worth pointing out because that's happening.
What the hell?
Well, I don't know if Scott told you, this might be relevant because it's similar. When we opened up the key to the problem set 7, right? It was different.
Different than the
Than
problem?
what it actually was. Like Alex opened it up on his thing and I think Jonathan had it up on his little tablet and it was right. It was the real one that Scott saw before because when Scott looked, it's like this isn't what was there before. It's different, and I couldn't open it up. I don't know what happened.
We're using the same computer?
It looks very similar.
This isn't the one you're using.
No.
Oh god.
No, because I was using 3.5.
Let me record this. I'm gonna have to try it.
But I'm wondering, how can I put this in MATLAB to solve it for me instead of going through the messy algebra?
Don't you know how to use MATLAB to solve systems equations?
Yeah, I know, but yeah, I know how to do that. But matrices,
Yeah.
How do you put this in matrix, this equation?
Well, how many unknowns do you have?
One.
Do you have 2 equations and 1 unknown?
No. This is okay. This is when I actually simplify it after because I didn't know how to do the MATLAB, so I just got each and divided by 96.
Yeah.
And
Well, you know, this is no longer. You only have a 1 equation, 1 unknown, so it's not really a matrix problem. It's just an algebra problem.
So how can you put the algebra in?
Just solve it algebraically and use MATLAB for the calculation. I mean, you could. MATLAB doesn't have. I mean, MATLAB I think has a solve function, but we only have FreeMat here. Oh no, you have MATLAB. Well, there's a way to set up an equation and use solve. I haven't used it in a while.
I feel I'm trying to build a function so I can solve that.
No, I don't think so. I think you just type help solve, help MATLAB solve, MATLAB help solve or something. It's in the symbolic toolbox. If you have the student version, I think you have.
I have the MATLAB, not the student version.
You have the professional version of MATLAB?
Yeah,
Okay.
like $100 one. I don't know if it's the student version or not.
I think that's the student version.
Because it was like $50 a student.
Well, they have ones with different toolboxes, but I think yours should have the symbolic toolbox. So you set up the equation as a function of x. You can just use x where you have Thevenin, and then solve x equals solve, and it'll actually give you the solution.
Nice.
Yeah, so let's just do a simple one,
Yeah.
like
Okay, cool.
say
you're in the script right now.
you say sins x. So where's the command line? I want the command line right here.
Yeah, you.
Sims is for symbolic,
Mm-hmm.
and see if that actually works. It might take a while. Okay, it worked. And then you say
You
equation
equivalent.
equals, something like 25 minus x. And then you would just say,
You want to set it equal to something before you solve? Because they did set it equal to 1.
right.
So, 0 or something? It should be 2 of equal, I guess. Yeah,
Yes, you're right.
2 of. That's so cool. Okay, now we say solve or something? Okay. Nice.
Yeah,
Cool.
yeah. So try that. That can help.
So we did nodal.
Little analysis. That works. Okay, so V1 minus V2. You just have a V2 node, right? There's only one unknown node.
Yeah,
Right?
and V2 is equal to V10.
Yeah. So 0 minus V2 over 463 plus 12.4. No, that's an error there.
Yes?
Yeah, that's not 12.4 there. That's a floating voltage source.
Oh, that's right.
Now you could do a supernode, but
Turn it into a current
just
source.
call that V3. I would call this V3 here.
Okay.
There's a node there. See, or you can easily figure out what this voltage is relative to ground, right? Because you have KVL here. You can find it real easily. Can you see it?
Like KVL in here.
Yeah. Well, KVL, this, like if you hook a voltmeter up here, it's sitting on top of two voltage sources. If you don't see that, just call that V3.
Okay.
And then you could do a supernode for the V1, V3, and then do a by inspection equation. You have to do the currents going, but you have another voltage source here, though. So let's see what we could do there. I think you would have to basically combine both of these into one giant supernode.
Could I turn this into a current source? And we just do it?
You could, but it's right. You can't actually. You didn't do. Let's see. The node for V2 is good because you don't have any voltage sources. We know this voltage. You got to get this current here going through R3, but it's got to be V3 minus V2 over R3. It's not 12.4 because this is not attached to ground here, right? This would only be 12.4 if there was a ground right here, but it's not. You see what I'm saying?
Because would this be 12.29 plus 12.4?
Yeah, that's what I'm trying to say.
Okay.
Yeah, good. Yeah, and when you see that, it just makes it trivial. I mean, if you don't see that, then you could do KVL here and do a proof that way, but. So you got that current going there, that current going there, that current going there. That'll help find Thevenin. Yep. Anyone else have any questions? How's your Thevenin going?
Yes.
You did mesh?
Yeah.
Good. Did it come out okay? You're not sure?
I'm not sure.
Did you measure it on your circuit yet?
No, not yet.
Okay. Looks like a nice arrangement there.
Because when I do, I try to model for spell, but it kind of have to be like a really big denominator. So.
Yeah, it's a little tricky for nodal. You can do it, but it's mesh is probably a little simpler.
Mm-hmm.
So you got that plus 980 times by 1. Yep, and then you got yeah, that looks good. You found I1, I2, and then Thevenin is going to be times I2, right? Yeah, that looks good. I think that looks right. Yeah. So now you can try firing up your circuit. See if that is the equivalent. Cool. Good luck. Questions, anybody? You're doubting yourself? You're not sure it's correct?
Because they got like a different.
What'd you have for the answer?
So for V1 turned on, I got 8.9.
Uh-huh.
And V2 turned on, I got 5.1.
Let's add this together and you got 13 or something?
14.03.
What'd you get, Matthew, for Thevenin?
Well, when you were saying to David that this voltage here is actually a combination of these two, I changed, like I had this whole equation set up, but I had a 12.45.
Oh, you did? Okay, yeah, so that's going to work. Yeah, that's
But then I plugged in that and I got like 10.61 or something.
That's pretty close to what...
is that what we expected?
That's pretty close to what Hong has.
Okay. I tried to do a
So Hong is the closest thing to PSpice we have.
Okay.
I got 10.4 or so.
Yeah, it should be something like around.
Okay, I don't know what I did wrong though.
So you've got, with V1 turned on, is this V1? You should have 471 over this parallel plus 471 times that. That might be okay. And then with V2 turned on, you've got 12.3 times. What was the parallel combination of these two? Oh, you got 471 here. But it should be 149. So the 149 plus 91. So the parallel is the that is the R that you're measuring the voltage across.
So we 149 over 9.
149 plus 91, yeah.
Okay.
That would probably help.
Okay.
Okay over here? Any questions?
Oh, when we take these out, do you want us to put them back in these?
No, I do not want you to put them back in there.
Okay.
Just leave them loose in there. Some people just,
Gotcha.
I don't know, maybe at the end when I said put everything back the way you found it, they thought
That's
I
what
did
we've
it
been
circular.
doing. I've been putting them back in this thing.
Yeah, it's not necessary. Don't bother doing
Okay.
that. Just leave them in the bins.
Yeah.
And the bins are supposed to be in. Questions? How's your Thevenin coming?
Oh yeah, I got it. Right.
Looks good?
Yeah.
Yeah?
Yeah.
You too? You're good.
Yeah, we're comparing.
Good to know, yeah. Your values are slightly different though, right?
Just about like.
Because you're doing your own with your own components?
Yeah.
It's
almost close though.
Yeah, it should be a little different, but. Questions? Yes?
I get 8.35.
You're getting 8.35, and it's supposed to be 10 point something, right?
10.45.
That's not good. So when I look at your circuit, this 1K resistor looks like it's dangling. This end isn't connected to anything. Is that supposed to be true? Isn't that supposed to be connected to something?
Yeah, this one should connect to this one.
Okay.
Yeah.
Okay, but it's not.
Yeah.
That'll probably help. Yeah. And there's a question over here. Let me just get your question real fast. You still got the table up. On what this meant. So yeah, after you get your circuit working, right, you're going to put up 3 different loads. These are 3 new resistors with these values. You're measuring them, and you're going to plug them in as the loads. So based on your Thevenin, you're going to use the voltage divided equation on your Thevenin model and figure out what the voltage should be. You know that part. And then you're going to measure it, figure out the error, and calculate power for each resistor. And then you're going to build, so you can do that for all 4 of these things, and then you're going to build an R Thevenin and a 50 ohm resistor out of multiple resistors.
Say that last part again?
So the last part is, first just do it with the single resistors, and then to get a couple different values, like the R Thevenin value, which is going to be, should be the maximum power one, you're going to build an R Thevenin by combining these resistors in the same series parallel that they are in your circuit. So you can build a load resistor that has almost identical resistance to your Thevenin model.
Oh, using the ones that we have?
Well, you're going to pick 3 new resistors of the same values that you're using in the circuit, and you combine them in a way that gives you a net resistance of R Thevenin. And when you do that, you should get the biggest power there. But then you can make a 50 ohm resistor to get a smaller one out of a 100 ohm resistor, two 100 ohm resistors in parallel. So you construct those, measure those net resistances, and do the same calculations on that.
So we might need to change this because we don't. This is too small to be putting
a load across.
To be putting multiple.
Well, you could just add. You could just pull out like the space where AB is to separate points here. You can put a little jumper wire to here and jumper wire to there.
Right, we just jump across.
Yeah.
Okay.
And you have more space to put multiple resistors across. The most you'll need to put across there is 3. It takes 3 to build R Thevenin.
Okay.
Okay.
Calculated V7.
Table 3.
Yeah. So for a given VL voltage divided equation.
In this table?
Yeah.
You're going to do it both. There's a column for calculated.
Calculated VL.
Yep.
So voltage divided equation.
Yep.
Which I believe is this.
Using your Thevenin model.
Yes. Yep. And so for V Thevenin, are we using the calculated V Thevenin or the measured V Thevenin?
They should be really close. How far apart are they?
It was like 139 versus 131. 1.14%.
Yeah.
No, V Thevenin was 0.02%.
Yeah, 0.02.
They're off by 0.02%?
Yes.
So it almost doesn't matter.
Yeah.
Yeah.
But our Thevenin does actually, because it's 1.14%.
It's off by how much? 1.4?
1.14%.
Well, yeah, I think for VL, stick with your model values.
Okay. And then same with our Thevenin that we're putting in.
Yeah.
Okay.
You know, the problem is when you measure resistors with an ohmmeter, they have a different amount of current flowing through. When you have them in a real circuit, then they have more current and they tend to warm up, and so they change resistance values. So that's why you do get a discrepancy. And you know, it should be fairly small, but yeah, stick with just the model. Unless you're more than 3% off, then you know, switch over. But
Okay.
probably stick with the model. It's good.
Okay,
Yeah.
thanks.
Any questions? Is that working better?
Yeah, I got 40.
Yeah, that's great. Very close. Yep.
Yeah, lucky. Small.
So you've got a short circuit for the power supplies,
Yeah.
and now you've hooked up a ohmmeter to it. Your R Thevenin, I think, is kind of big. Let's see. How'd you calculate R Thevenin? R3 parallel with R1 plus R2. Show me. So when these are off, let's see.
So this is just a no, right?
Mm-hmm.
So it should be
And that's a
power.
short, and that's a short. I think that's right. What you have there, I think, is correct. So you have an error in your calculation.
Okay.
Yeah, you want to try tracking it down? I'll let you try to figure that out. And I'll come back if you have any problems. Questions?
I have issues with upright boards.
Okay.
So
Because now
I'm not sure if I did this correctly. So
Did you measure voltage and not getting the right number?
yeah, I got like a -2 or something.
like this is
Okay.
right. You know, this could be since they're connected vertically and have my negative in here. Now I can make this row ground. Right? Yeah. Could be that. Yeah.
So
Because I like
let's
the
see.
layout, but it's just kind of
Get creative with it.
it's hard to like tell where things are.
So this is your looking at the circuit over there, and this is your 220, right?
Mhm.
And according to the circuit, that 220 is supposed to have one end connected to the plus 12 of V1 and the other end connected to the 470 ohm resistor. And I see that point here looks good. You got the 1K and you got the 470 going to ground. And there's your, that's 12 volts going there, right? Yeah, that looks good. So your 220 looks okay. And you have a wire connecting to the minus sign of V2. And the plus side of the V2 is going to the 1K resistor.
Right.
Yeah. The 1K resistor is interesting here because this looks like it's dangling. You have a resistor that has nothing else connected to it. That's not the same as it is in the circuit over there.
Oh, okay.
Yeah.
So you have this thing where you've got, this is the second V2, the plus side of the V2 source. And you've got it connecting to, it looks like you've got it connecting to this node. Like your voltage source plus here is connected to there. Do you see that? So this is your plus, and it's connected to all these guys because of this jumper wire there.
Okay.
And this there, yep. So I think this is connected wrong. I think you need to move this this orange wire somewhere else.
Towards this end right here.
Towards which end?
The 1K. And make that connect to the negative. I mean the ground. Or no, the positive.
Uh-huh.
Okay.
You see that?
Yeah. Okay.
That's better.
What am I measuring is from here to here. So I have to move this one too also.
You're measuring, well, look at that again.
Oh, the one.
This point here, where does this point here correspond to your circuit?
Right here. Does it?
Are you sure? Look at this point and tell me what's all connected to this point
Oh,
on
no,
your
no.
circuit board.
The V2 center right here.
Yeah, you see how you can do it? You got to make those correlations.
So this should be here.
Okay, where is this again? Point to this on your circuit schematic.
Right here.
Yeah, but you're supposed to be measuring what? You're supposed to be measuring VAV, right?
Mm-hmm.
So putting it over there isn't going to really help you measure VAV, right? You want to leave it between here and here.
Well, between this nose, or
Is it right?
yeah.
Right, because this point here is where all these three resistors come together,
Okay.
and that's ground.
Right. Measure it.
Any questions?
We're working on this V7, and we hooked it up incorrectly, we believe.
You mean your V7 voltage is not right?
Yes.
But you already, wait.
No, for measuring
For measuring it.
For measuring what?
of our Thevenin.
You mean for measuring the load, VL, when you have a load of R Thevenin on it?
So this is our logic here. We got the R Thevenin from just taking R1 in parallel with R2 in parallel with R3.
Uh-huh.
So we put all those in parallel again.
Yep.
But I think just our node, we're confused about nodes.
Okay.
About how to hook that up. How to hook the parallel resistors into a single resistor here. I think we have that messed up.
You do have them all connected between the same two nodes, which is good.
Yeah.
And this point where they're jumping in is where these three resistors come together, which seems correct. So
We measured it by having these two things just stick out, and we just measured the voltage drop across that. Does that make sense?
voltage drop from
The ground. Oh, because this is the ground and this is the ground. This is the wrong node. That's why. That we need to measure this. This is VA. This VB is the ground. So we were just measuring the ground from the ground.
Oh, were you getting 0?
Yeah.
I see. Well, that would do it. Yeah.
Bingo.
Good.
Thanks, Tom.
Yep.
Thanks for listening.
I didn't do anything. Yeah. Just having someone listen is all it takes. Sometimes.
Sometimes.
Should equal 5.254.
2.7.
Yeah. There you go.
Decent.
That's what you want. So you've got a Thevenin load there. All working out okay?
Also,
Sure. I mean, it doesn't have to. I'm more interested in just getting the layout. Yeah. Right. Cool.
So is this a right formula? VH square over 4.
Uh-huh.
Okay, because there is a different formula in the lab.
Really? What does the lab say?
It's missing the 4, I guess.
Ooh, really? Wait. Yeah. Shoot. Thank you. I'll fix that on the data sheet, right? Okay. Thank you.
Basically,
So for this one, do I have to do the measure RL?
Sorry.
What I can do,
You're going to create an Thevenin, an RL that's the same value as Thevenin.
parallel to 100 ohm parallel.
and if it's like, I mean, if it's
Uh,
throughout the day, then,
Let's see.
This one, I mean, step 11
Oh,
or step 12?
12.
12, yeah. You're going to take two 100 ohm resistors, put them in parallel. Yeah.
So do I have to do the measure or because we don't have like a so
Yeah, you're going to take 200 ohms in parallel and measure that combination with your ohm meter. So you can stick two of them side by side on the breadboard and then measure it with your ohm meter. So like right over here, you could just take 200 ohm resistors, put them in parallel. They're there. And then hook up your ohm meter to it, and that'll should give you 50 ohms. Mm-hmm. There we go. 50 ohms. Yep. Mm-hmm. Yeah, so that's your combined resistor. Questions, anybody?
Yeah, I have a question. So for step number 11, so I'm getting a totally different value for BL. And everything was fine so far, which is, but I don't know if I'm doing something wrong.
Yeah,
Anyway,
something
we have
must
to
be
connect
wrong
the
there,
three.
because it should be a lot closer than that.
Yeah, so this is where I connect the three resistors in parallel, which are
Okay.
supposed to be the same. So this is like my A and my B. And yeah, they are connected.
Wait a second. That doesn't look right, right? That's 100. This should be 470, right? That's 100 ohms.
Oh, okay.
Yeah, you got the wrong resistor there. Yep. You have to start charging money for those questions. Question?
yeah, number 11.
You're trying to construct this one? Are you getting the...
So I didn't even start.
So what you can do is, you did this one though, right? Okay. Well, you can make a resistor that's very close to our Thevenin by selecting 3 new resistors with those values and put them in parallel across the terminals A, B. So you just take these 3 resistors. So we don't have a 130 ohm resistor, but if you take a 1K, a 470, and a 220, put them in parallel, you're going to get pretty close to 130.
Okay, do the same thing as 12, basically.
Yeah, but with 3 instead of 2.
Okay.
Yep. And you should get very close to our Thevenin. How's it going? Any questions? Hmm. 3 o'clock, you got 1 more hour. Anything I do?
What are we supposed to do down in this part of it after we?
Yeah, so you're measuring the power at a lot of different resistor values. Wouldn't it be nice to know if it's true that you really get the maximum power when you have the load equal to R Thevenin?
Oh, okay.
So there's a slot here for R Thevenin. See step 11. You're going to construct a composite resistor out of multiple resistors. So you take a 1K, a 220, and a 470, put them in parallel. That looks like R Thevenin.
Okay.
And then you're going to measure it and see if you truly get the maximum power there.
Like this?
Yeah. So that's like that. 3 resistors. Point them again. Point to those resistors. Yeah. So that's your RL, which is close to R Thevenin.
I don't have a lot of space.
Well, you could extend 2 wires out.
Yeah.
To be to the point where you attach them.
That's what I'm gonna do.
I don't know why it's popping at 0.
What's 0?
It's on voltage.
You're measuring voltage? Well, you don't have any power hooked up.
Oh, that's why.
So I'm trying to figure out like how can I make that diagram to this.
How do you do what?
This diagram onto this, like measure each of the resistors on the breadboard. VL.
Yeah, so you are going to use that model to do your calculations, but this circuit is going to remain the same.
Same, yeah. So let's try to figure out how.
So you're gonna put these resistors into the AB point.
Okay.
That's where the load is. So if you scroll up, this point here, I should have labeled it AB, but that's the Thevenin equivalent. It's the equivalent of that point there. We're attaching the load to point AB.
Okay.
And
Yeah. And then I have to put the load one.
yeah, I need to put an AB there. It would help
So I get
between
that,
the
but
AB
I'm trying to
terminals.
figure out where do you put that resistor on the board?
Well, the point where you measured voltage,
Mm-hmm.
to measure the Thevenin voltage, can you show me where that is?
Right here, point AB.
Yeah, right here. That's point AB. Well, that's where you have to put the resistors in between these 2 points. Now, if you can't do that easily, because your circuit doesn't really make that easy, you could plant this somewhere else, like maybe even here. And since this is just ground, if you attach them between here and ground, that will be between A and B, because this is connecting you to A. Right?
Okay.
So you take,
Oh, so the other end of the resistor would be V.
yeah, B is ground.
Okay.
So it would go right there.
All right.
So one there and one there. One in there and one in there. And then just measure the voltage across that resistor.
Okay.
I have a question, Tom.
Yep.
So when we put these 3 in parallel, this is our Thevenin resistance.
Yep.
Right? And so are we trying to, like, we have our circuit here that's our Thevenin equivalent, and we want to test our loads.
Yep.
Does that mean that when we're inputting them on this table, we're taking like another 100 ohm resistor and like putting it in parallel with these 3 or something? Like, I'm confused about what's going on with this part of the table and like what we're supposed to be doing right here.
Well, this resistor is a composite consisting of a 220, a 470, and a 1K in parallel, which is sort of the same formula that you use to create this effective resistance here.
Right.
You can detach this and see if that's true by hooking up this to an ohm meter, which is kind of what we're doing in these steps here. You want to measure the resistance of that resistor. And
the Thevenin one?
Yeah, of your load, that's a Thevenin, and it should be close to 130.
Yeah.
Then what that means is you're putting in something here into a circuit that has a Thevenin resistance of the same value. Meaning the voltage across that should be your Thevenin voltage divided by 2, because it's a simple voltage divider, and you're at basically the midpoint with both resistors being the same. You should get close to V Thevenin over 2 across that load.
So
then that will allow you to calculate the power through this combination resistor.
okay, but I don't. So what are we doing on these three then? If this is like,
So
okay, never mind.
whatever you did for these guys, right? You had a calculated VL from your model, your Thevenin model, using the voltage divider formula. Knowing what this is,
right? Then you can get the.
you can put that into your Thevenin model and calculate what the voltage should be, and then you're going to measure it and see. Again, they should be very close.
Okay.
But your power here should be at the max, because that is what the maximum power transfer theory says.
Okay.
And then you do it once more with a
50 ohm.
50 ohm resistor constructed of two 100 ohm resistors in parallel.
How are you measuring the resistance across? Because I have the two hundreds.
Well, you have to make sure that they're out of the circuit.
Out of the
And
circuit.
are you in ohmmeter mode? It says OL. Do you have the power hooked up? That's bad. So when you're measuring ohms, when you're measuring resistance, you can't have an active circuit.
Gotcha.
You have to have the resistors disconnected from the circuit, and now you got 50 ohms. Yeah. Questions?
From step 12 and 11.
Pardon me? Do I need a picture from step 12 and 11? No. No, that's good. Thank you. You all finished? Great.